In this last week of the reactive programming course, we will focus first on something which was implicitly there already, namely that actors as independent agents of computation are by default distributed. Normally, you run them just on different CPUs in the same system, but there is nothing stopping you from running them on different network hosts, and we will do this in practice. This means if you picture, for example, people who are living on different continents, that it takes some effort for them to agree on a common truth or a common decision. The same thing is true for actors, and we call this eventual consistency. After that, we will talk about scalability and responsiveness and how you achieve these in an actor-based system, rounding up all the four tenets of reactive programming, which were event-driven, scalable, resilient, and responsive. Actors are designed to be distributed, and in this lecture we will see an example of that using the Akka cluster. In order to fully appreciate how far actors take us when it comes to distribution, let us look at what the impact of network communication is to a distributed program. Compared to communication within the same process, by calling methods, for example, we will experience several differences when doing that over the network. First of all, the memory is not shared anymore. Data can only be shared by value because a copy will be made. The object will be serialized, sent over the network connection, deserialized. Therefore, the object will not be the same. We have seen that a stateful object is one whose behavior depends on its history. But the history of the copy at the other side of the network will not be the same after a while than the history of the object on the originating node. This has the consequence that only immutable objects can be sensibly shared. Other differences include that the bandwidth available for communication is a lot lower when you traverse the network, and the latency for all communication is quite a bit higher. You cannot transfer a network packet in a nanosecond, but you can call a method in a nanosecond. Together with the need to serialize and deserialize objects instead of just passing along their reference, this makes the difference even more severe. But in addition to these quantitative effects, there are also new things which can happen. When you send a message over the network, it might just not arrive, or it might arrive and the reply might not come back. Thus, there is the possibility for partial failure. A part of your messages might arrive, for example, and you cannot know which ones that were until you get the reply back. Another kind of failure is that data corruption can also happen. I know from personal experience that when you send data down a TCP connection, for example, you will see about one corruption event per terabyte data sent. Running multiple processes on the same computer and having them communicate, for example, over the localhost interface, makes some of these differences less severe in number, but the qualitative issues stay the same. The overarching description of the problem is that distributed computing breaks the core assumptions made by a synchronous programming model. We have talked about actors for quite a while now, so you know that all of their communication is asynchronous, one way, and not guaranteed to arrive. Hence, they model precisely what the network gives us. You could say that instead of taking the local model and trying to extend it to the network, actors took the inverse approach, looking at the network model and using that on the local machine. The next feature of actors is that they run so fully isolated from each other that from the outside they all look the same. They all just actor refs. Regardless where they live, it would be the same sending a message to them. This is what we call location transparency. The current semantics and feature set offered by Akka actors have been reached by rigorously treating everything as if it were remote, and all features which cannot be modeled in this world were removed. As a result, the effort of writing a distributed program using actors is basically the same as the effort of writing a local variant of the same program. The code itself will not look much different, as we will soon see. Before we can witness actors talking to each other over the network, we need to look at how that is done under the hood. We know that actors are hierarchical, and every actor has a name in the namespace of its parent. They form a tree, just like a file system. Let's say we have an actor here named user. This is Akka's guardian actor for all actors you create with system actor off. And this one creates a greeter. This is the same as a file system having a folder called user and in it a folder called greeter. All actors can have children, so they are all like folders and not like files. When you run this program and print the path of this actor ref, then it will show you this. All paths conform to the URI format, the Uniform Resource Identifier. This one has a so-called authority part, and a path. In Akka, the authority part is used to display the address of the actor system. In this case, we created an actor system called Hello World, and the Akka scheme, so the Akka protocol, designates that this is a local actor path. Then with slashes, we separate the path elements, so user is this actor, greeter is this actor. We want to talk about actors which use the network, so we should also look at a remote address example. Here we have an Akka system using the TCP protocol, also named Hello World, at some IP address or host name, colon, and then the port at which it listens. This description is enough for any other actor system to send a message to any actor within this one. It will just open a TCP connection to this IP address and port and try to connect to this actor system should it respond at that. We've seen here two examples, a local address for the greeter and a remote address, which for the greeter would look like this. This means that every actor is identified by at least one URI. It could have multiple if, for example, the actor system is reachable by multiple protocols or on multiple IP addresses. Up to now we have mostly worked with actor ref, and the newly found actor path has some relationship to actor ref, which needs to be properly explained. Actor names are unique within a parent, but once the terminated message has been delivered for a child, the parent knows that the name can be reused. It could create an actor which has exactly the same name, but it will not be the same actor. The actor ref will be a different one. Therefore, keep in mind that actor path is just the full name of the actor, and the actor path exists whether the actor exists or not. An actor ref, on the other hand, points exactly to one actor which was started at some point. It points to one incarnation, we say, of the actor path. An actor path also has a tell method. We will see that later. So you can send it messages. The difference is, since you don't know that behind this actor path actually an actor exists, it cannot be watched. You need an actor ref if you want to use lifecycle monitoring. In the end, the difference between an actor ref and an actor path is just one number. We call it the UID of the actor incarnation. If you print an actor ref, it looks just like the actor path, but with a fragment part added, which is this UID. When communicating with remote systems, it is necessary to talk to actors which you have not created and for which you have no means to acquire an actor ref. You just know at which host and port the actor lives, what the system's name is, and where the actor lives in the hierarchy over there. To support this, the actor context has another method called actor selection. You can pass in any actor path and it will construct something which you can send to. It's the only operation it supports. And there is one message that every actor automatically handles, and that is aka.actor.identify, imported here, which takes one piece of data, a correlation identifier. You can use anything you want. This little actor here, the resolver, will perform the job of resolving an actor path, if possible, to the actor ref of the actor which is currently living under that name. So sending the identify message with the pair of path and current sender will result in us getting back an actor identity. In the positive case, where the actor is currently alive, we get this one with some reference, so we can tell our client that we resolved the path and this is the actor ref of the actor currently. Otherwise, the actor identity message will contain none. This procedure reflects that communication is necessary in order to determine whether an actor exists or does not exist. This is why no actor refs can just be fabricated from thin air. They must be obtained by using identify from paths, if there is no other way to obtain them. Actor paths do not have to be absolute. They do not need to contain all the actor system's address information. They can also be relative to the current actor. When we say context.actor selection and give a relative URI without a leading slash, then it will be interpreted to the current actor's position in the hierarchy. In this case, if the current actor has a child actor named child, and that one has a child actor named grandchild, then this actor selection will select it. Just as in a file system, you can use ... to signify the parent at any point in the selection. If the selection starts with a slash, its anchor will be the system's root guardian. So you can resolve actors which live somewhere near the top of the hierarchy and where you know the exact name of all parents. Finally, actor selection also supports wildcards. So you can, for example, send a message to this actor selection /user/controllers/* to send to all children of the controller's actor. The ability to send to a name instead of to an actor ref is exploited by the aka cluster module, which we will look at next. First, what is a cluster? A cluster is foremost a set of nodes of actor systems in this case, and this set is defined such that all members of this set, so all nodes of the same cluster, have the same idea about who is in the cluster and who is not. It is like a group of people where everybody knows everybody else, and foreigners are known to be foreign. This group of people can then collaborate on a common task, and the same can be done between actor systems. Let's say we have some actor systems, some nodes A, B, C, D. And these four all have the same idea that they four form a cluster. Now if we have another node here called E, and this node thinks it forms a cluster with the other four, then the set of A, B, C, D, and E is not a cluster, because not everyone in this set agrees upon who is in the cluster. Cluster membership can change over time, of course, and A, B, C, and D might learn of E's existence and finally accept E into the same cluster, and then the cluster would have size 5. We'll see how that works in a minute. Clusters are formed in a form of inductive reasoning. It starts with one node, which basically joins itself. It declares itself to be a cluster of size 1. And then any given node can join a given cluster to enlarge that cluster by 1. This is achieved by sending a request to any current member of the cluster. And then information is spread within the cluster that this new one wants to join. And once all the current members have learned of this, they agree, okay, it is a good idea, let's accept it in. One important property of the Akka cluster is that it does not contain any central leader or coordinator, which would be a single point of failure. Information is disseminated in an epidemic fashion. This gossip protocol is resilient to failure because every node will gossip to a few of its peers every second, regardless of whether that was successful or not. So eventually all information will be spread throughout the cluster. Let's see how this works in practice. For that we need one more dependency, which is the Akka cluster module. And in the configuration, we need to enable the cluster module by saying that the akka.actor.provider must be akka.cluster.clusterActorRefProvider. This configures the actor system to use a different mechanism when creating actors. All calls to context actor_of are in the end handled by the actor_ref provider. And the cluster one supports a few operations that the local one cannot, as we will see. There are several ways to apply this configuration. For example, you could add a file named application.conf to the class path, which contains this snippet, or you can use Java system properties like that on the command line. Next, we need to write a new main program. This actor, when it starts up, obtains the cluster extension of the system, subscribes to some events. This in the end works the same way as the event stream. And finally, it joins its own address. If you remember, the first step in forming a cluster is that one node must start it off. It must join itself. Then, in the behavior of this actor, we wait for member up events for which we registered. And if the member which just joined is not the current one, then someone else joined, and then we can do some interesting stuff. The default configuration of the remote communication module is that it will start listening on port 2552 using TCP. To make this exercise interesting, we need, of course, a second node. Since all actor systems will need to listen on a TCP port, but only one of them can have the port 2552, we need to configure a different port for the cluster worker. Setting the port is done like this with the property akka remote neti TCP port, and setting it to 0 means to pick a random one. We don't need to know at which port the cluster worker lives, because it will just join the main one. The address of the cluster main can be derived from this worker's self address by replacing the port with the number 2552. And then the worker joins the main. In this case, we registered for receiving not member up, but member removed events. And whenever the address of the removed member is the main one, so when the main program shuts down, this also stops. With these two main programs, we can, if we run them, observe that they will join, but nothing much will happen. We need to define some actor which makes use of the cluster. For this, we are going to modify the well-known receptionist to spawn the controller actors not locally, using context actor of simply as local children, but to run them instead on cluster nodes which are not the current node. How does that work? First of all, the receptionist needs to know who is in the cluster and who is not. Therefore, it subscribes to member up and member removed events. And when it stops, it unsubscribes itself. In response to cluster.subscribe, the actor will always receive first the current cluster state. And this current cluster state has a members list. I convert these members to a linear sequence from a set and map _.address over it to extract all the addresses of the cluster nodes. Then from these addresses, I filter out the self address, so whatever remains is not myself. And if there is another node, so not myself is not empty, then I change to the active mode. But typically, when the receptionist is started, that happens quite early in the program, the cluster has not yet been formed, so typically the current cluster state will contain no members. Therefore, there is the second case, that upon member up, if that member's address is not my own address, I change to the active state with the vector of size 1 giving just that member. While awaiting members, we have no computing resources in order to perform the task of getting a URL, for example. So during that time, we reply to the sender that it failed because we have no nodes available. The active behavior will also have to monitor the cluster, because after all, members can be added and removed at any point in time. When more members are added, again, which is not the self address, then we just change to the active state with the addition of the newly known address. And when members are removed from the set, we filter it out from the addresses, and if that was the last one, then we go back to the awaiting members state. Otherwise, we continue with the reduced list. Now we get closer to the interesting part, using the information we just obtained. In the active state, when a GET request comes in, we look whether the currently running requests, that is context.children.size, is less than the addresses we know about. Otherwise, we have one request running per cluster node. Let's say that is the limit, and then we reject it. But if it is the first request which comes in, that will always work. So we copy the client, that's the sender, of this GET request. Then we pick an address randomly from the list and extract it here. And then we create a new actor, a customer, which I'll show in the next slide, which gets the client, the URL, which is supposed to be retrieved, and the cluster address where the work is supposed to be performed. Please note that these two lines are necessary because the actor creation described in here runs asynchronously. Props describe how to create an actor later. Therefore, it is subject to the same restrictions as with future callbacks within actors or scheduled actions within actors, as we have seen last week. Finally, the customer actor. This one is responsible for making sure that the given URL is retrieved, but the work is supposed to be performed at a remote node whose address is given here. For that, we need to create a controller. We have props controller here. Props, as I said, is a recipe for how to create an actor, and what we have used so far is the default behavior of creating an actor locally. But it also supports giving other arguments. Here we say with deploy, and then a deploy that is a description of how to deploy the actor. You can modify several things. One of them is the scope in which it shall be deployed. In this case, it is a remote scope. We do not want to create the actor on the local node. We want to create it on the given node whose address is here. This is the only change which is necessary to perform the work on a remote node. The call to context actor off then looks just the same, gives back an actor ref. Sending to this actor ref looks just the same, but this will go over the network now. Context.watch controller will watch this actor also over the network. But the call we make here looks exactly the same as in the local case. There is one more detail in this actor which needs special explanation. It is this line here. Whenever a message is sent, for example here, to another actor, we know that the self-reference of the enclosing actor is automatically picked up and passed along as the sender reference. This customer actor here is an ephemeral one. It is one which is not supposed to be seen from the outside. What this line does is it changes the meaning of who the sender of messages of this actor shall be. This implicit value is also of type actorref, and it is available in the current scope, which takes precedence over implicit values found in the actor trait. Therefore, all messages sent by this customer will appear to have been sent by its parent instead. Since the consequences of this remote deployment are not visible in code, let me draw a diagram to show what happens. The whole program starts because we instantiate the cluster main application actor. We need to mark out in which actor system that happens. This is cluster main and its guardian actor. The app then goes on to create the receptionist. And when a request comes in, this one will create a customer. Up to this point, everything has been local. But the customer deploys the controller into the cluster workers system. So we need to draw that as well. This system also has a user guardian and an application. But this application does not do anything besides waiting for the termination of the program. This system has another thing which is interesting here. It has a remote guardian. And when the customer deploys the controller, what it really does is it sends a message to this one to create the controller for it. This one will first create a folder so that it can keep actors deployed from different other systems, and within it, it will create a marker for that it was user app receptionist customer and so forth. And then it will finally create the controller actor. These here are not really actors. They are just names inserted such that the controller can be found for remote communication. But the controller will be the child actor of the customer logically. So when in the controller we say context.parent, the message will go here. Then, as in this link checker example, it will spawn getters as needed during the retrieval of the URL. Now that we have successfully remote deployed the controller, we just need to supervise it. As usual, there was the receive timeout, in which case we unwatch the controller and say the retrieval has failed because we didn't get anything in time. Note that deathwatch works exactly the same, even though the controller is remote deployed, so in that case we also give a failure message. If we get back a successful result, again we unwatch and send back the successful result. And then whatever happens after any of these three has occurred, we need to stop. And this stop is recursive, so once this parent actor is stopped, the controller is stopped with it. We need to explicitly annotate the type of this partial function literal here, because Scala's type inference would not be able to figure that out without help when it comes to the and-then combinator. I have loaded these actors as well into the Eclipse project so that we can try it out. First, here you see the cluster worker with the code that you already know. Note that the web client will now be called in the cluster worker, so this is where we need to clean up the resources of the async web client. The cluster main is like the original main program, but it has been adapted as shown to watch for cluster events and to join itself in the beginning. And in the behavior, when we receive the member up event and the member's address is not our own, then we know that there is a cluster worker. So I've written a small function getLater to use the system scheduler to send a GET request to the receptionist after a certain delay, which is given here. So after 1 second, we retrieve google.com. After 2 seconds, we try 2 parallel queries. One of them should fail because there's just one cluster worker. And then we try 2 more. In the run configuration for the cluster main, I have set the necessary option to switch on the clustering support. And here is another option which can be set. You say the cluster shall not start unless there are at least 2 members. For the cluster worker, as mentioned, we need to configure the remote port to be automatic. And then there is one more option which I set, which is called auto down, which I will explain in the following. So we run the cluster main. It starts up, informs us that the node AKTCP main on port 2552 is in the joining phase, but nothing has happened yet. When we start up the cluster worker, the program will start to run. And now it is finished, so we can look at the logs. This was the line which we had already seen. Then the cluster worker running on this ephemeral port is also seen as joining. Then here it says the leader is moving node 2552 to up and the other one also to up. I told you that there is no single point of bottleneck in AK cluster. although it does have a leader. This seems to be contradictory, but it is not so. The leader is not elected. It is not one special node. Any node can be the leader, and it is just statically determined by the set of node addresses. They are sorted in a certain format, and then always the first address, which is in the membership list, will be the leader. And since everybody agrees on who is in the list and on the sort order, everybody will see the same as the leader without the need for communication. Once the nodes are up, the program goes on to retrieve the page from google.com. Then we launched 2 queries in parallel. One of them gets rejected by too many queries. The others are successful. Finally, we had modified the main program such that it will shut down after the retrievals have all been performed. So the leader is moving itself first to leaving and then to exiting states, and then the whole program shuts down. There is some communication afterwards between the nodes. In the end, first this one shuts down, and the other one has also automatically shut down. This one has gone via a different route, which I will explain in the following.